Okay, shall we start? Do you remember those people who raised their hands and they said they're advanced? Now you get homework. Okay, so I will work with the people who are beginners for most of the afternoon. Okay, and for the people who are advanced, I will give you a job after we finished playing with this tutorial. Okay, so here's the plan. Now I will go through this tutorial and show you a few games of how to set it up and how to have different kinds of post-processing data, look at the graphs and various other things that come with that. By then you're going to have ParaView. Okay? Then I'm going to show you how to use block mesh, and I will ask you to build a geometry for a backward-facing step. Okay, by the way, for that I need a whiteboard. Can we scribble on something, or shall I just do it on the screen? No? Okay.
Yeah, the smartboard there.
No. Yeah. We'll just do it on this with some sort of graphing tool and find out what we can do. Okay? And for the people who are advanced, among the tutorials there is one called engine cooling. Okay? What I need you to do is to convert the star CD mesh, run the simulation. When you're finished, then create a scalar transport foam case and run a transient simulation tracking the scalar from the inlet to the outlet to find out how the domain is filling. And if you're really advanced, then show me how to calculate the residence time as well. Okay? So that will keep you amused for a couple of hours, and in the end we will do it quickly. Okay? So to start with, let's do a few things with the NACA 0012 case. I have slightly changed the parameters to make my pictures look pretty, but basically it is the same case that you have. So the first thing that I will do is I will run potential foam. If I don't know what the options are, I can say minus help, and then it will tell me things like minus reset U, minus write P, minus parallel. Okay, so I will start with potential foam minus write P. And as you can see, it says create time, create mesh, reading field P, reading field U. It solves the potential flow problem, and it calculates the velocity field. When it calculates the velocity, it will calculate the P from the condition of P plus half rho U squared equals constant. So now in the time directory 0, I can find a field which is non-uniform. Okay, and here you can see some distribution of the pressure and also some distribution of the velocity. Let's do some basic post-processing now. So my profile is here. I will use a cutting plane in the Z normal direction. And on that cutting plane, I can draw some vectors. Here, I switch it to vector. 0.2 is a reasonable size, still too big. 0.2. I can color the vector by glyph vector. And down here, I can say, show me all the points of my vector field. Okay, still too big for my taste. 0.05. And here, you can see what my vectors are doing. Okay, this is potential flow, so there is quite a clean attachment point. What are they? Oh, there we are. Okay. So that is a bit pretty. Okay. When I have done with that, under System Control Dictionary, I will enable the forces function object. Okay, which says, calculate me the forces on the patch wall with the center of reference and rho infinity of 1. You remember what I told you about the density? Okay, so the incompressible solvers are divided through by the density, but for the density, I want for the force, I want the density. Okay, so here I can specify rho infinity of 1 to allow me to calculate the density, the force out of the kinematic pressure. The solver is simple foam, and the other thing that I want to show you is the relaxation factors. 0.3, 0.5, 0.5. Typically you can run 0.3, 0.7, 0.7, but usually with these tutorials people mess about, so I keep it a bit more conservative than necessary. Simple foam, pipe, T log. Will show me my residuals, and as you can see, this is nicely converging. Okay, the residual that you're looking at is always the initial residual. Okay, so what is going on here? When you formulate linear equation sets for each of your equations, and you call the linear equation solver, it will solve those equations. Okay? But that doesn't indicate overall convergence, because your equations are coupled to each other and they're also nonlinear. So what we do is we go round and round in circles and keep on solving them again until things stop changing. When your fields stop changing, your initial residual will drop below 10 to the minus 4 or 10 to the minus 5, depending on the definition. So the fact that the final residual is low does not mean that I have converged over the nonlinear terms. Okay? So, as you can see, the residuals are going nicely down. I solve for the pressure twice. This is called using a non-orthogonal corrector. Okay? For those who know about non-orthogonal correctors, don't use more than one. If you have to use more than one, your simulation is so slow and your mesh is so terrible that you're better off building a better mesh. Okay. By now this should have converged. And you can see here it says reach the convergence criterion 10 to the minus 3 in 595 iterations, which means that the biggest number of 5 10 to the minus 6 blah 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 is less than 1 10 to the minus 3, and that says your solver has converged. Okay? In many cases, you will see the pressure being the last variable to converge, which is quite typical for the segregated algorithms. Okay? You remember how we switched on the function object for the force in the control dictionary. Okay? That produced the output in forces in the 0 directory. Okay? And here it will say time, 10, 20, 30, 40, forces. Pressure force, viscous force, moment, pressure moment, viscous moment around the point 0, 0, 0, and you can follow what these forces are doing. With Foam Extend I have a little tool called plot forces, which will create an XY graph of your forces by removing all these brackets. Okay? This is usually a good measure of convergence. So around here, say 400 iteration, my force is pretty well stabilized, and I can declare that my simulations has converged. Also, this is 2D, so the Z force will be 0. Okay, shall we do some visualization? Again, para foam minus native reader. Okay, I will read all the mesh components. I will zoom in on the profile. And now I will visualize something like K. And guess what? My K field is uniform. Okay? Every now and then I have people who ask me, well, where are my results? Can you tell me what's going on? Time? Zero. Well, if you're looking at zero results, you're not going to get much. In the pressure and velocity field, I ran potential foam, so they are not completely uniform, but this is not really my result. So clicking at this button over here takes me to the last time step. And where are my results now? Well, I have to rescale. Okay, so now here you can see peak K. If I show you the velocity field, it is going to be a bit nicer. If I show you the pressure field, it is going to be even nicer. Okay, now, the second thing that I need to do is visualize some vectors, etc., because this is what my boss likes. Okay? The first thing is pick out the surface patch. Okay, so filters, alphabetical, extract block, for me ended up here. Give me the wool patch. Here's my wing. And you can see the pressure distribution or the turbulence kinetic energy distribution on the patch. Now this looks okay, but there is one parameter that I always want to check. You know what? Y plus, have you heard of Y plus? Okay, so we are using the K epsilon model with the wall functions. The dimensionless distance to the first cell must be calculated. Okay? It isn't here, it isn't on my list of fields. Okay, so if I click here, there is no choice of Y plus. So in order to calculate it, I will go back to my case and say something like calc Y plus RAS. And look what it does. It says reading field U, reading field U, calculating incompressible transport model, patch 0 names wall, Y plus between 9 and 83, which is acceptable. Now I can jump into a different time step, and suddenly I have this Y plus field to visualize on the surface of my airfoil. Okay, so now people tell you, yeah, but your Y plus needs to be between, say, 30 and 80, but here you have Y plus of 9. Well, yeah, I do, because in the impingement point, my Y plus is always going to be very low because the velocity goes to 0. And at the trailing edge, where my flow does something silly and the mesh does not adapt, my Y plus is going to be silly. I don't care. What I do care about is whether Y plus is okay over the bulk of the profile. Okay? So here it is around 45, which is perfectly fine. Okay. The second thing that I want to do is visualize some vectors. Okay? So I'm going to jump back onto NACA 0012, do a cutting plane, Z normal, Y. I usually switch off the whole plane, because otherwise if you grab it, you move it. Okay, and again, I can go scaling, all points, 0.002, apply, color them with glyph vector. Okay, and here is a nice picture. Okay, the third thing that I want to do is I want to visualize the pressure gradient. How am I going to do that? Okay, so part of you probably has got a button saying give me a field and then calculate the gradient and show me that, but I don't want that one. I want my gradient to be consistent with the way that I'm working in discretization. Okay? And there is quite a lot of things like that that I want to do, and in older versions of foam we had little executables for each one. Okay? So magnitude of the velocity, or Q criterion, or entropy, or gradient, or magnitude of gradient, divergence of the flux, blah, blah, blah. And now we replace all of those with one tool called foam calc. Okay? And the way it works is you go foam calc minus help, and then it say, well, I want one of the calc types which are defined here. Okay? Add, subtract, components, div, mag, grad, etc. Okay? So what I can do is foam calc mag grad p, and for each of my time steps it will say reading field p, calculating mag grad p. Now if I change the time step again, here among the fields on the slice I also have mag grad p. Let's get rid of some of this other garbage and rescale. So my mag grad p is really big here, but I can change the maximum to be 2000, and now the whole thing looks a bit prettier. Okay? Now, we said this is an incompressible flow, right? And my phase representation of the velocity is my phase flux. So if I want to make sure that everything is okay with my solution, I will do foam calc div phi. Okay, give me the divergence of the flux. But now I don't just want div phi, I also want magnitude of div phi. So now that I have created myself a field called div phi, I'm going to do another one called mag div phi. And changing the time step here allows me to visualize mag div phi. Zoom out. And as you can see, this is basically zero. Okay? You will get a little bit of numerical garbage like this, but the divergence of the flux is zero, which is okay for an incompressible flow. Okay. What other things would you like to see with this case? Any ideas? No? Well, in that case, I'm going to give up. And I'm going to give you your job. Okay, so what I want you to do is to create me a geometry that looks like this. And it is a backward-facing step. The flow will come from the left-hand side. It will come out of the right-hand side. The top and the bottom patch will be zero. Okay? So what I expect to have is a recirculation region somewhere around here with the flow going around. Okay? And in order to do that, we will use a mesh generator that comes with OpenFOAM, which is called block mesh. Anyone used block mesh before? Nobody else? Or everybody? No? Okay, so let's just say a few words about block mesh. So the block mesh will create a single block that looks like this. Oops, it is. I think I killed it. Okay, so a single block will look like this. I'm not going to try a dotted line again because it might kill it. By creating points which are numbered as follows. Zero, 1, 2, 3, 4, 5, 6, 7. Okay, and then we will specify the number of cells in the direction of 0 to 1, the number of cells in the direction 0 to 3, the number of cells in the direction of 0 to 4. And when we want to define the outside faces of this block, we will create them based on these points. Okay, let me give you an example of what a block mesh dictionary looks like. Okay, so the first entry will be convert to meters. If you want to work in millimeters, that is 0.01001. If you want to work with meters, it's 1. After that, you will define the vertices as the x, y, z coordinates for the block. And then for my cavity, which is the easiest geometry made out of one block, I will define a block in terms of these 8 vertices. Remember, the vertices go into the positive right-hand rotation, 0, 1, 2, 3 in the back plane, 4, 5, 6, 7 in the front plane, and I will define 20 vertices in the x, 20 vertices in the y, 20 cells in the x, 20 cells in the y, 1 cell in the z direction, and currently we are not going to worry about the grading. Okay, so let's go back to my sketch and define some locations of the points. Oops, that's the wrong one. Okay, so my geometry should look like this. Okay, and I need some dimensions. So here I'm going to have L equals 1.5. Here I'm going to have H equals 1, sorry, 0.5. here I'm going to have L equals 8, and this point here will be 0, 0, 0. Okay? In terms of the block structure, I can only define the blocks that meet face to face. Okay? So my block number 1 will be this one here. Block number 2 will be this one here. And block number 3 will be this one here. Okay? So to define my points, I will start counting from 0 and go 0, 1, 2, 3, 4, 5, 6, 7, and then you're going to have another plane of points like this, right? So, when I define my mesh, my block number 1 will be 2, 3, 6, 5, and then another plane. Okay. My next block will be 3, 4, 7, 6, and my third block will be 0, 1, 4, 3. Any ideas? Are you with me, or do I need to pull out some slides to show you how block mesh works? Slides? Okay, so this is my lid drilling cavity tutorial. Your geometry is slightly different. I want to have my mesh, which is 0.1 by 0.1. This will be one patch, and these three will be another patch. First, I'm going to define my points of the block. 0, 1, 2, 3, 4, 5, 6, 7. And then we can start looking at the block mesh dictionary. Okay, do you see the points? 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. So these are the points of the block. Then 0, 0, 0, 0.1, 1, 0, 1, 1, 0, 1, all moved into one plane. Okay, defining the block 0, 1, 2, 3, 4, 5, 6, 7, because I ordered my points in the right way. And then finally, defining boundary patches. Okay, so the first one says moving wall. This is the top. Take a look at my block. Okay, so that would be 2, 3, 7, 6, right hand rule. The other one will be that one, and that one. So something like 3, 0, 4, 7, 0, 4, 5, 1, 1, 2, 6, 5. You see them? Okay, do you want to see the real example of what I'm asking you to do?
So how is the normal sit? So you said the right-hand rule?
As my professor of mathematics would say, the rule of the left foot, or obviously the right-hand rule. You can start from any point and walk around into the right-hand
But the
side.
face should either, the normal should be outwards. So.
Yes,
So
your mesh looks like an angry hedgehog, so all of the arrows go outside.
okay.
Okay, so let's take a look at the real example of what I'm asking you to do. Okay, so this is my mesh for the block mesh, and I will say 0, 0, 1.5, 8. 0, minus 0.5, 0, 1.5, minus 0.5, 8, minus 0.5, 0. 1.5, minus 1, 0, 8, minus 1, 0. Okay? You see, this is like x, y, z, x, y, z, for 3 points in the first line, 3 points in the second line, 3 points in the third line, and then I move all of those in the z direction by 0.025. Okay, so let's correct my picture. Okay, so this one is 0. One, 2, 3, 4, 5, 6, 7. Okay, now I need another set which is exactly like that, but one plane in front of me in Z. So next to that I'm going to write another set of numbers, this time in blue, and I'll zoom the whole thing in later. So if this is 7, then next to 0 there will be 8, 9, 10, 11, 12, 13, 14, 15. Okay, so let's zoom this in a little bit. Okay. Okay. Now, can you see the blocks? So this block will be 3, 4, 1, 0, 11, 12, 9, 8. Okay, so let's take a look at the file. Three, 4, 1, 0, 11, 12, 9, 8. See? Then I say between 3 and 4 is my x direction. I want 40 cells, 20 in the y direction, 1 in the z direction. Okay? So here I have 40 by 20. What's the next block? You see it? 4, 5, 2, 1, 12, 13, 10, 9. Okay? Four, 5, 2, 1, 12, 13, 10, 9, 100 by 20. And the third block, 6, 7, 5, 4, 14, 15, 13, 12. You see it here. What about boundaries? Inlet. Is this side here. And it will be 3, 11, 8, 0. Okay. And outlet on the other side, how many faces?
2.
That's right, 2. So the first will be something like 5, 2, 10, 13. Okay, what happens if I go 2, 10, 13, 5? Nothing, it's the same face. Okay? The second face, 5, 13, 15, 7. Okay. Now a difficult question. Where do you start from? Okay, if I ask you to do one of these from scratch, where will you start from? Tutorials, incompressible, simple foam. There is something called bits daily. Copy that into your directory with everything. Then throw away the bits that you don't need and start editing the fields. Okay? Too scared? Do I need to do it together with you? Okay, let me show you. Okay. Okay. So my workspace is somewhere in the run unigent mkdir my cases. Okay. Then I type tut to take me to the tutorials, incompressible, simple foam, cp -r, bits daily into my cases, cd my cases, move bits daily into my back step. Going to my back step, open constant polymesh, block mesh dictionary, and throw everything away. Okay, ready to start? I said my first point . will be 0.0.0, 0, 0, 0. Next point, 1.5, 0, 0. Third point, 8, 0, 0. Next line, minus 0.5, minus 0.5, minus 0.5. Third line, minus 1, minus 1, minus, oh sorry, just 2 times minus 1. I usually do this, back plane, front plane. Define my blocks. I'm going to have 3 of those blocks. And the first one, as we said, is 3, 4, 1, 0, 11, 12, 9, 8. The second block is 4, 5, 2, 1. Twelve, 13, 10, 9. And the third block, 6, 7, 5, 4. Fourteen, 15, 13, 12. Okay, on the inlet, I have 3, 11, 8, 0. At the outlet, I have 7, 5, 13, 15. And 5, 2, 10, 13. For the upper wall, I'm going to have 0, 8, 9, 1, 1, 9, 10, 2. And for the lower wall, I have 3, 4, 12, 11. Now this one is tricky. 4, 6, 14, 12. And 6, 7, 15, 14. Okay, let's see, how did I do? Not bad, huh? You want to copy my numbers or you're working it out yourselves? Copy my numbers? Work it out yourselves? Cool. Okay, any problems with this mesh? Well, I'd like to have it a little bit less uniform. For example, I know that all of the interesting physics will happen here, right? So I would like these cells to be bigger than those cells, and those cells to be smaller than these cells here. Okay? So for that, I am going to use the grading option. Look here. In the block, it will give me the simple grading number, and that one tells me the ratio of the last cell size to the first cell in the block. Okay? So if I want the last cell to be 10 times smaller than the first one, I will set the ratio to 0.1. Okay? And on the other side, I have the last cell to the first cell, and I can set the ratio of something like 20. Okay, so 0.1, 20, 20. Okay, I screwed up. That's a bit too much, right? So let's check that one to 0.25, 10, 10. Okay, still not perfect, but pretty good. So I will do something like 0.25, sorry, 0.2, and here I will say 8, 8. And now this is quite pretty. Okay. So there is one thing that I smuggled past you without you noticing. How thick should the geometry be? Well, it doesn't really matter, right? Okay, but if you make it really, really, really thin, it is silly to look at the screen. And the second thing is, I have to calculate the volume of these cells, okay? So I want them to look reasonable, okay? So the cell aspect ratio of that cell is within, I don't know, 20 to 1, right? If I make my geometry this wide, it would be 1,000,000 to 1, and I'm going to have a round-off error in the calculation of the volume, okay? So there is no guidance really of how thick it needs to be. Just make it look pretty. Okay? What do we do next? Well, first let's visualize the patches. Okay? So I will look at that as an outline, and then I'm going to go filter, extract block. Sorry, my mistake. Filter, extract block, inlet. You see it? That's my inlet patch, everything is fine. Next, outlet. That's my outlet patch, everything is fine. Get rid of that, do upper wall and lower wall Everything is fine. What's the next thing that we do? Check mesh. Mesh non-orthogonality, 0 degrees, we made it perfect, right? The second thing is overall bounding box from minus 0.1 to 0 in the y direction. So if I want to calculate the Reynolds number, what will be my height of the step? 0.05. Okay, so now I can do constant transport properties and set my viscosity to 10 to the minus 5. That's fine. Okay, Reynolds number equals U times L over nu, and I want it to be 1E5. So Python 1E5 multiplied by 1E minus 5 divided by 0.05. My inlet velocity for the Reynolds number of 100,000 should be 20. Okay? Turbulence kinetic energy, 0.02% of 20 times 1.5 times that thing, 0.24. Okay? So, open constant polymesh boundary, and the patches that I have are inlet, outlet, upper wall, lower wall, and default faces. Okay? Open U. I want my velocity to be 20. Upper wall, lower wall. This one is called default faces, right? Yeah. Okay. Time to teach you some tricks, right? I want to initialize my internal field to 20 meters per second to help my solver converge properly. And then I want to say that the value at the inlet is the same as the value that I used for initialization. Okay? So what I can say is something like this. Okay, you see what happened here? Inlet value is my keyword for a dictionary, but I want to use it many times. So any keyword can also be expanded. Okay? So down here where I say internal field equals $inlet value, it says, well, grab whatever was under inlet value and use it, both at the inlet and the internal field. Okay? Now there is one additional trick that I want to teach you here to do with outlet boundaries. Okay, do we have people running Fluent? At least one, right? Do you know how Fluent tells you warning, inlet detected at outlet boundary blocking? Okay, so what happens there is if you have a vortex that goes through the outlet boundary, then it should create a backflow, and creating a backflow like that will destabilize the solver. Okay, so in foam, we want to use a boundary condition which will do the same, but we cannot talk about outflows and inflows about the boundary because the library doesn't know what equations it's solving. Okay, so for that we will use a special boundary condition called inlet outlet. Okay, what that does is it says if the flow is going out, use the zero gradient boundary condition as normally, which is what I would have here at the outlet boundary. But if the flow is coming in, then use the fixed value to a certain value. Okay? So let's just change it. Okay? So here I will say type inlet value uniform 0, 0, 0 value actually I just messed up a little bit. Okay, you see I have changed this from inlet value to in value because I can't have inlet value here and there. And then for the value, meaning the initialization, I will use this uniform 20, 0, 0. Okay, so for K, now I can do it properly and say something like, what did we say for the value? 0 to 4, right? Right? Okay, but this is also quite boring because if I have 200 patches which are all walls, I don't really want to do it like that. Okay, so what I can do is I can say, give me all the patches that start with something and end with wall. Okay, so rather than writing out the full name of the patch, I will use a regular expression. Okay, just for a laugh, I will try and guess how it's done. You know, is it star dot or dot star? Anyway, the code will tell us. Okay, so now that I'm set up, I can just run simple foam. And it says expected keyword, uniform or non-uniform. and I am up and running. Okay, so the point of this case was first to show you that with block mesh we can make simple meshes very quickly. And point number 2 comes up now, which is you have seen myself save 2 problems on the screen very quickly without telling you what's going on. Okay? So now let's make some deliberate mistakes, find out what the code says, and figure out where the error comes from. Are you ready? Okay. So what I'm teaching you here is to read the error messages. So first I will edit 0/u, and here in the upper wall value I will say value equals 0. You see? Do you understand the problem with that? So u is a volume vector field, and I said, well, your value is 0. Well, 0 is a scalar, and u is a vector, which means that the code cannot read this. Okay? So let's take a look. It says, phone warning, blah, 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 on file 0/u, from line 40 to 42, expect keyword uniform or non-uniform, assuming deprecated field format. What that tells you is that the previous version of FOAM, which had input-output format 1.0, does not understand what uniform and non-uniform is. I can find out that the word is missing, and I will assume that the previous one is okay. And then right at the bottom of the screen, it says, FOAM fatal I/O error, expected open bracket while reading vector space found on line 42, label 0. Got it? So it says, I'm in file 0/u on line 42. Okay? Line 42. It is exactly where I messed it up. Okay? So let's change this and say uniform banana. Okay? So what it says now is FOAM fatal I/O error expected and open bracket found word banana. Okay, shall we give it an open bracket? Will that work? No? Do I have to show you? Yes? Okay, so it says, expected a close bracket while reading vector space, found word banana, again, 0u boundary field upper wall value, line 42. Okay, so let's get rid of that banana. Okay, now let's do something more complicated. F3 schemes, default scheme, now it says, FOAM fatal I/O error, unknown discretization scheme banana, valid options are blah blah blah, in file system FV schemes, diff scheme, diff VU at line 32. Okay? Line 32, and here's my banana. Okay, let's do something even more complicated. Okay, I gave it negative dissipation of turbulence kinetic energy. What will help now? Any idea? Will it tell me in line blah 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 you gave me a negative number? No, because the library doesn't know that the field epsilon can only take the positive numbers, but the code will crash. Okay? In fact, it won't, because I stabilized it so much. Okay, so let's do something more drastic, like 0. Still can't crash. Sorry, can't kill it like that. Any more ideas? How can I kill the code? Okay, let's do something with discretization. And that is going to kill. Will that kill it? Unknown RAS model type banana, and even better, it will tell me it failed on it will not tell me. RAS model new. Okay. Okay, so I guess the message here is try and read what the error message says, and most of the input-output messages will be picked up for you, okay? And if there's something strange going on, and the code will even give you the options, okay? I was really hoping that negative epsilon is going to kill it, but it looks like everything gets bounded on the way in, and then even that doesn't make it fail. Okay. Now I have a job for you. Okay. In the tutorial cases that we had, there is one called engine cooling block. Okay. I will take you through the first steps. Okay. Run engine cooling. And here, in the ProStar directory, there is the old format *cd files. Okay? Now, because this is an external format for mesh conversion, FOAM will not automatically unzip the gzip files, which means that you have to do it yourself. What I need you to do then is to use the tool called *to-FOAM, convert the mesh into OpenFOAM format, do a check mesh, and tell me what's wrong with it. Okay, I'll give you 5 minutes and then I'll come back to do it again.